Here's our first set of notes for Unit 5, Energy, Work, and Power. We'll start with the scientific definition of work. Work in science is defined as force times distance. Now, there is a caveat to that. It's only the component of force that is parallel to the distance. So, for example, if I have a box and I'm pulling it with a string, but I'm pulling it an angle, only the parallel component would count as doing work. The vertical component or the perpendicular component would do no work if my distance were horizontal. If we think about the angle between the force and the distance, then I could rewrite this as work equals force times the cosine of the angle. That's going to give me this adjacent side, this parallel value, times the distance. And more usually, you'll see the formula written as work equals FD cosine theta. The next thing we're going to do right off the bat is we're going to apply this to a spring. And what's interesting about a spring is that as we stretch a spring, we exert more force. So the farther we stretch the spring, if I stretch the spring a little bit, I exert a little bit of force, and if I stretch the spring farther, I'm going to exert more force. And it turns out that this is actually a linear relationship. So I can sketch a graph. Force measured in newtons will go on the vertical axis. And stretch, or change in position, so if we start here at 0, this would be x. How far do I stretch it? Be measured in meters. And some springs stretch right away when you pull on them. In other words, that Y-intercept is 0. And the formula that defines this purple line is F equals kx. So that means that the slope of this line is k, which is called the spring constant. And we can define that slope as the change in force over the amount that the spring was stretched. The Y-intercept, some springs behave a little bit differently than this. Some springs take a minimum amount of force to get them to stretch at all. In that case, the graph looks kind of like this. Oops, let me try that again. So we have a non-zero Y-intercept. I can write the equation here as F equals the initial force plus kx. In this case, the meaning of the Y-intercept is the amount of force needed to get the spring to stretch. And we're going to measure that in newtons. Okay, next, let's think about the area. Let's think about the area under this graph. So let me zoom in here. So I've got a force versus, I've got a force versus position graph. And to find area, I'm going to multiply those two variables together. But what did we just see about multiplying force and position or distance? When we multiply those two things together, we get work. And actually, the area under this graph is going to be the work done on the spring, and it's going to be the energy stored in the stretched spring. Let's think about how we could compute that. If I pick a point on the coordinate plane, I would call that point xy. And in this diagram, I would go over x and up. We're used to thinking of up being y, but in this case, up is not y. Up is the vertical axis is the force, and the force equals kx, which means this point up here is over x up kx. And if I wanted to find the area of this triangle, I could do that by finding the area of a triangle. The area of a triangle is area equals 1/2 base times height. But the base, as we saw, was x. Oops. And the height is kx. So 1/2 x times kx is 1/2 kx squared. So that is the formula for the work done on the spring and the formula for the energy stored in the spring. So underneath this third spot here for the meaning of the area, I'm going to say that the area means the work done to stretch a spring. It's also the energy stored in a spring. So if I think about this diagram that I have up here up top, when I stretch out the spring and if I hold it, that spring has the potential to move if I let go. And so the type of energy that's stored in the spring is potential energy. The symbol for potential energy in AP Physics is U. Okay, and then the next thing we've got here is derivation of the equation of energy stored in a spring. Well, we did that up above. The energy stored is equal to the area, which is equal to the area of a triangle, 1/2 base times height. Again, the base of our triangle is x. The height of our triangle is kx. And when we simplify that, we get 1/2 kx squared. So I can write that potential energy stored in a spring is equal to 1/2 kx squared. So now let's use that idea to solve an example. Suppose a spring has a constant of 50 newtons per meter. Write Hooke's law for the spring. So I'm going to write that F equals kx, or F equals 50 newtons per meter times x. I should pause for a minute and point something out. Technically, Hooke's law is F equals negative kx. And the reason for this is that Hooke's law is for the spring, not for the person pulling the spring. So if I go back to my example up here, if I look at my spring and I think about pulling on it, my force and my distance are in the same direction. They are down. But the spring is not pulling down. The spring is pulling up. So because the force produced by the spring is opposite the distance, the spring actually does negative work. Now, It's not very convenient to graph that in the fourth quadrant. So typically what we do is just use the absolute value because it's easier, and then we can graph things in the first quadrant like we've done above. Okay, let's take a look at this question B. How much more energy is stored when the spring is stretched from 0.3 meters to 0.5 meters? To solve this, I'm going to sketch a graph. So I'm going to put position on the horizontal axis, and I know that this goes to 0.5, 2, 3, 4, 5. So this, I'm going by 0.1s there. On the vertical axis, if I use the formula I just created, F equals 50 newtons per meter times X 0.5 meters, I get that F is 25 newtons, which means at 0.5 meters, I've got 25 newtons, and I should be able to draw that graph. The slope here, again, the slope is 50. If I take the rise over the run, I get 50, which is what the slope is. The answer to this question, how much more energy is stored, is a question of area. We want to know how much energy is stored in this part of the graph. So there's a couple different ways that I can solve that. I could find the area of this outer triangle. I'll color it in purple here. The area of this outer triangle in purple would be 1/2 kx squared, or 1/2 times 50 times 0.5 squared, and that would be, let's see, 6.25 joules. Oh, by the way, energy and work is measured in Newton meters, and a Newton meter is a joule, named after James Prescott Joule. Okay, that got me the whole outer purple triangle, and now what I need to do to solve this is I need to subtract off this blue triangle. So I'm going to do the same process, but I'm going to change the x value to 0.3. So now I've got 1/2 times 50 times 0.3 squared. So we get 2.25. And when I subtract those things, I get 4 joules of energy. And I'll switch colors here. This 4 joules is just this area. Of course, that's not the only way to solve that. That's not the only way to find area. And I encourage you to think about what you've learned in previous math classes. This yellow figure, or this figure that I keep shading in, I love it so much, it's trapezoid. It's a trapezoid turned on its side. It's got 2 bases. This base is 25, and the other base is 15, and the height of this trapezoid is 0.2. And another way to solve this problem is to find the area of that trapezoid. Again, this trapezoid is turned on its side, so the bases of a trapezoid are the parallel sides, are vertical. So the area would be 1/2 times 0.2 times 15 plus 25. Really what this is doing, by the way, is it is taking the average of 15 and 25, which of course is 20, and it's kind of like taking this triangle up here and rotating it and flipping it and putting it there, so that essentially what we're doing is finding the area of a rectangle. So everything reduces down to a simpler figure. Okay, anyway, 1/2 times 0.2 is 0.1, and then 0.1 times 40 would again give me 4 joules. So I get the same answer either way. All right, stay tuned for more interesting information about energy, work, and power.